Hey there, welcome. So, have you ever stopped to think about what connects you, the chair you're sitting on, the air you're breathing, and even the most distant stars? Well, it turns out everything, and I mean everything, living or not, is built from the exact same fundamental building blocks. We're talking about incredibly tiny particles called atoms.
And when I say tiny, I am not kidding. Just look at this number, 100 trillion. What is that? Well, that's roughly how many atoms are packed into a single one of your body's cells. It's just a staggering number, right? And this is our jumping off point, our gateway into the incredible microscopic world we're about to dive into.
Okay, so if trillions of these things make up everything, how does that even work? Well, to get our heads around that, we've got to start small. We need to look at the basic blueprint of just one single atom. Let's get into it. So an atom basically has two main parts. Right at the very center, you've got this dense, super-packed core called the nucleus. And then, whizzing around that nucleus, you have these even tinier particles called electrons. They're constantly moving, orbiting in layers that we call shells. And this leads to something that's, well, it's kind of hard to wrap your head around. See, just like our solar system is mostly empty space with planets orbiting a sun, an atom is pretty much the same. It's almost all empty space. Get this, the nucleus, the part with nearly all the mass, is about 10,000 times smaller than the entire atom. It's wild.
All right, so what exactly is in that tiny nucleus? And what are these electrons zipping around? It's time to zoom in even further and meet the three key players, the subatomic trio that makes up literally every atom in the universe.
Now, before we get into the nitty-gritty, here's a super simple way to remember their electrical charges, because it can get a little confusing. Just remember this. Proton starts with P, so it's positive. Neutron starts with N, so it's neutral. It has no charge. And that leaves the electron. Well, it's the one that's left, so it has to be negative. Easy, right? Okay, this table lays it all out perfectly. You can see that protons and neutrons hang out together in the nucleus. And look at their mass. We just say it's 1. They're the heavyweights, which means pretty much all the atom's mass is packed into that tiny center. But then you have the electrons, out in the shells. Their mass is so small, it's practically zero compared to the others. Tiny, but they carry that all-important negative charge. So you've got this situation. Positive charges in the middle, negative charges on the outside. And in a perfectly normal, stable atom, it's a perfect balance. The number of positive protons is exactly the same as the number of negative electrons. They cancel each other out completely, so the atom has no overall charge. It's neutral. But what happens when that perfect balance gets, messed up?
Well, that's when an atom becomes something called an ion. An ion is really just an atom that's no longer neutral. It's either gained or lost an electron, and that simple act completely throws off that delicate balance we were talking about, leaving the whole thing with either a positive or a negative charge.
So how does an atom get a positive charge? It's actually a little counterintuitive. You start with a neutral atom, right? Protons and electrons are equal. Then that atom loses a negative electron. Think about it. If you lose something negative, you become more positive. Now there are more positive protons than negative electrons. And boom, the atom is now a positive ion.
And you guessed it, the opposite works too. Let's say our neutral atom gains an extra electron. Well, now you've got more negative charges than positive ones. The balance tips the other way, and the atom becomes a negative ion. It really is all about whether it's gaining or losing those tiny electrons.
Okay, let's put all this knowledge to work. Scientists have a really clever shorthand for describing different types of atoms, what we call elements. It's like a secret code that, once you know how to read it, tells you everything you need to know.
Let's take this one for example. This is the symbol for an element called lithium. Now, I know it might just look like some letters and numbers, but I promise you, those two little numbers hold the key to figuring out exactly how many protons, neutrons, and electrons are in this atom. Okay, first things first, let's look at the bottom number, that 3. This is the atomic number, and it is, without a doubt, the most important number here. Think of it as the atom's social security number, or its unique ID. It tells you the number of protons. If an atom has 3 protons, it is always lithium, no exceptions. It's literally what defines it.
All right, now let's look at the top number, the 7. This is called the mass number. And it's pretty simple. Remember how we said the protons and neutrons were the heavyweights in the nucleus? Well, this number is just the total count of both of them added together. So for our lithium atom, the total number of protons and neutrons is 7.
So, wait a minute. If the top number is protons plus neutrons, and the bottom number is just the protons, how do we figure out how many neutrons there are? Any ideas? It's actually just a little bit of simple math.
It's this simple. You just subtract. You take the big number on top, the mass number, and you subtract the smaller number on the bottom, the atomic number. And whatever is left over, that's your number of neutrons. That's it. So let's put it all together for our lithium atom. The bottom number is 3, so we know it has 3 protons. We're assuming it's a neutral atom, so the electrons have to balance the protons. That means 3 electrons too. And for the neutrons, we just do the math. 7 minus 3 equals 4. So we have 4 neutrons. And just like that, we've completely decoded it.
And this really brings us to the single most important point of this whole explainer. If there's one thing you remember, make it this. The number of protons is an atom's unchangeable identity. You can add or remove electrons to make ions. The number of neutrons can even change sometimes, but the number of protons, that's fixed. If you change the number of protons, you haven't just changed the atom, you've changed the element into something completely different.
So we're left with this one last kind of incredible thought. Everything you can see, everything you can touch, from a single drop of water to an entire galaxy of stars, it's all built from different arrangements of just these 3 tiny particles. So the real question is, how? How do just 3 simple building blocks create the infinite complexity of the entire universe? That's a story for another time. Thanks for joining me.